Hello, friends. Okay, so now we're going to get into some quantitation. As I mentioned in the last lecture, we're looking at protein ligand interactions, and we define a ligand as something that reversibly binds to a protein. And so by reversible, it means it can come on and it can come off. Typically, what that means is that this is non-covalent interactions. Although we'll see you can have some temporary covalent interactions that occur. But generally, this means non-covalent interactions. And so if we look at this just as a chemical formula, this would be the protein as P plus the ligand as L, which can either form or unform a protein ligand complex, PL, right? And if we remember from our good old chemical equilibrium, we can quantitate a K for this. And so we can have a K for the association that is equal to the concentration of the protein ligand complex, which is the product in this reaction, over the concentration of the protein, free protein, plus the concentration of the free ligand. And I'll say this is here, the A stands for association complex, right? Our constant. We've seen a Ka before that deals with the acid dissociation complex, which is just some like ridiculousness that we do in biochemistry that I really don't understand. And so here the Ka is for the association, right? So we're going from disassociated to associated. Now we can flip this, right? And simply say if we take the inverse of this, which is the PL over PL here. This is simply kind of taking this reaction backwards, and we define that as a KD. I'll put this a little lighter. So this is a KD. Maybe this is a small d there. Um, which is just the disassociation of a protein bound to a unbound. And we're going to see this both ways coming up, so I wanted to kind of introduce this now. Looking at this Ka real quick, one of the things that we can do, and we'll see why we do this in a little bit, let's just kind of go here. Ka is equal to, what did we say it was? PL over P times L. And so one of the things we can do is simply solve for PL. We'll see why a little bit later, but just to do our kind of basic algebra here, and this is what I learned in sixth grade, so I'll do it here. We want to solve for PL, we just kind of cross multiply and divide here. So PL would be equal to, in this case, Ka times P L there, right? So we can define the associated complex PL, at least the concentration of the associated complex, as the concentration of protein times the concentration of the ligand times the Ka. And that's going to be important later. All right, I think we now have all the tools to do a little good old-fashioned derivation. Again, one of my favorite things. So I'm trying to keep this under 10 minutes. I have 6 minutes less left, so let's get moving. All right, so we can define a theta here, and this theta is simply the fraction of bound protein that's bound by ligand. So that's what we're calling the saturation here, right? And with any fraction, a fraction is a part to a whole, right? So this is the part of the bound ligand to the whole. And the whole would be simply the bound protein plus the free protein, right? So total number of binding sites are going to be the bound plus the free. And obviously, the amount that's bound is going to be the bound, and that'll give you the fraction of what is bound. So, as I said before, using the equation P plus L goes to PL. We can define a Ka that would be equal to PL over P times L, or we can define a KD that is the inverse of that, free P, free L over PL. Okay, so I think we have all the tools, right, that we need in order to do this derivation, right? If we're looking at theta, oops, I forgot to erase this. So theta is the fractional saturation, and it's equal to PL plus PL plus free protein, right? But we have a definition of PL, right? The concentration of the bound protein is equal to the Ka of the free protein times the concentration of the ligand. And so if we use this definition of PL into this equation for theta, we get theta is equal to KALP over KALP plus the free protein. And if we, let me make this a little bit brighter. If we remember from our good old laws of distribution, we can actually pull out something from this equation. And the only thing we can pull out is the p's. So this would be equal to p over p times KAL over, what is this? KAL plus 1. All right, you see that? This is just kind of laws of distribution. P over P obviously cancels. And so we're left with theta equal to KAL over, oops, KAL plus 1. And we can now, since Ka is a constant and it's not a variable, we can also pull that out to come here, right? So theta is equal to L over L plus 1 over Ka, right? So we simply kind of divide both sides of this quotient by Ka here. So we have to, I'll make this a different color. So divide by Ka, divide by Ka, divide by Ka, right? And in this case, K is canceled there, K is canceled there, and we're left with this expression. Theta is equal to L over L plus Ka, 1 over Ka. And remember, the inverse of the Ka is the Kd, and so we can simplify this to be theta is equal to L plus L over L plus Kd, right? So this is great because we have now reduced this complicated term that has 1, 2, 3, 4 variable, oh, well, one, two, 3 variables to one that is one variable, the ligand concentration, and then a constant, the Kd, that is constant for the individual reaction, right? So here we are able to define the amount of protein that is bound to the ligand solely as a function of ligand concentration, at least as at a constant concentration of protein, right? This is a beautiful thing. We've gone from 3 variables, which would be impossible to figure out, to just one variable, the ligand concentration, and a constant, which is a function of the nature of the interaction between the protein and the ligand that is there. So we can now use this equation, and mind you, you can see this is not a linear equation, right? Because you have this L over L plus KD here. And we can use this to plot out the fractional saturation. And since I'm coming up on time, I'll talk about the implications of this plot later on. But there is a hell of a lot of good stuff that is coming. I'll holler in the next go round.